Hello there again. Uh, I hope you can hear me good. So let's get straight into it. The last live stream we had done a lot of tensor operations and stuff. A few of them are left, and probably the most important one is still left. That is broadcasting, which will be used all over the uh, deep learning frameworks, right? And broadcasting isn't something new. It's already there in NumPy, and we're just gonna do it in PyTorch, but principles almost remains the same. Okay, but few of them are few operations were left, so I'm gonna uh, walk them through. So the first one is concatenation. Basically, there are two tensors, and you just wanna concatenate. You wanna join them. So what you will do? So this is the code. Actually, already I've run it. So basically, there are this is tensor one, this is tensor two, x and y, and all you do is concatenate both of them, right? And so in default, if you hover over this, you see that concatenation dimension is 0. That means it's along the rows, right? So all you are doing is taking both of them and literally stacking them upon each other, right? That's all. Um, and let's see a few other examples with concatenations to completely solidify this operation. So there are three tensors, and I'm doing the same thing here, but I'm also defining this time dimension equals to 0, which is the default one actually. And if you run this, it just stacks all of them into one big uh, 6 by 2 tensor, right? That's all. But if I change this, if I change it to 1, so all it will do right now is uh, concatenate along the column. So it will just stack them up along the line, a horizontal line, right? So that's all it's gonna happen. So now it's 2,6. It's pretty simple, right? Uh, yeah. Then coming to few other examples, concatenate. Okay, concatenation. So this one I'm adding unsqueezing. If you remember from the last live stream, unsqueezing is basically adding one into in this case we are adding one dimension into the first position of that shape, right? So x I will just show it, it, it's really hard to sometimes just do this. So I added one more dimension into it. Okay, if you check out the shape, it was 2 by 2, but now I added one in the first position. This is the position. Okay, it defines the position, not the one. Okay, if I add 2 here, if I add 2, it will add that one into the second position. So you see that. Yeah. Okay. Okay, so I'm squeezing all of them and just doing along the columns. Let's see what happens. Okay, that's what you got. So original one look like this. When you concatenate along the first dimension, you see one thing. The one that changes is uh, this one. The 2, 1, 2. The dimension which has 1, that is the one that is changing to 3. So it's very easy to understand, and at the same time maybe you can just remember what's how it's all gonna change, right? For example, this one, this is 6, 1, 2. So in this scenario, if you can see, um, if you remember when we did for the normal one, this one, if it this is also 0 and this one is also 0, let's see. Okay, all it did was take this one. In this scenario it was 2 by 2, and we summed them up along the columns, right? We just stack them up along the vertically, and then this one we are just doing the same thing, but here we have it's a three-dimensional tensor, right? So here also you see this dimension is along which we are what do you say, concatenating. Okay, and if I go this one here, 1, then along this, so these two are being changed. The last one is kept as it is. Cool. I can show you that too. I mean, there's one more example that can come up. This kind of stuff, even I forget at times how it exactly works, why it works, and sometimes I have to refer back to the documentation and all. Okay. This is the one. Let's editable, scrollable. Okay. This is the tensor. The x1 has been changed to 2 comma 2 comma 1, 2 comma 2 comma 1, 2 comma 2 comma 1. Here when we were squeezing it 1, it became 2 comma 1 comma 2, right? In this we are doing it in a different way. Okay. And the reshaped versions are being printed here. You see this one. So it's 2 comma 2 comma 1, 1 column is there. That's it. Uh, okay, then we are concatenating along the row or the first dimension, right? Along the first dimension, we are concatenating it. So which one is the first dimension? Concatenation is done along two. Okay, wait, format. Okay, I think it's, I was testing some things out. I'm concatenating along dimension 2. There are 3 dimensions, right? 0, 1, 2. So let's see what we got from here. So after changing, see, it changed this one along this last dimension. It added all of them up. So it was 2 comma 2 comma 1, all of them, but we changed it to 2 comma 2 comma 3. So if it were 1, what, how it would change? So if you see now, 2 comma 6 comma 1. Why? Because we are changing along the second dimension, right? So keeping all the things same. See, one thing you need to understand is the number of elements will always remain the same. Okay, for example, the number of elements in this is 2. This has 4 elements, this has 4 elements, this has 4 elements. That is basically 12 elements are there, right? And all the if you do along the along the 0 dimension, first dimension, second dimension, this element will always be 2, sorry, element will always be 12, right? So if you see, the multiplication of this will always be 12, no matter which dimension. That's also one way to look at it, actually. If I do 1, is basically the first dimension, this dimension, along this dimension we are concatenating the whole thing. Then we again get 2, because it always has to come up to 12. It's easier to deduce what would that dimension change into. Okay, for example, I don't know, it's 2 into 2 into 2, right? Okay. Mm, mm. Okay, I suppose now you have an idea how to just see that instead of going and seeing the tensors, you can analyze what would it change into by just knowing the number of elements inside tensors. Because you know the shape, then you just multiply the shapes and you will get the shape of the actual tensor, and this operation can be done. Okay, that is it for concatenation. Now let's go with stacking. Stacking and concatenation kind of remains the same. I think so. One of the most important difference between concatenation and stacking would be that stacking adds one dimension to the tensor. Like concatenation does not add any dimension, extra dimension. I mean, so the original tensor were 2-dimensional. The resultant tensor is also 2-dimensional. But stack, it does add some dimension. It does add one more dimension to the final tensor. Okay, so here we go. Let's take x and y. Let's take the same x and y's that were there. If you remember, these two guys, where are they? These and these 2 by 2 matrices, or 2 by 2 tensor. And let's do this. Okay, simple. Now here, if you see, again the default is 0. We are stacking it along the second dimension only. But have you seen, although it's been stacked like that, but it added an extra dimension. If I were to print out the dimension also, stack tensor dot shape, you can see it's 2 comma 2 comma 2. It added an extra dimension. That is a property of stack that you need to be careful about, I suppose, at times. Okay, and let's see a few more examples related to this one. Okay, again, the three tensors, 2 by 2 tensors, and we're stacking them up along the first column, along the first column in this, as it is a matrix, so it would be along the rows, right? Uh, then checking out the shapes and what it looks like. The shape it's changed into 3 comma 2 comma 2. Again, same principle works here. The number of element will say is remain the same. 3 comma 2 comma 2 is 3 into 2 into 2. That's again 12, right? Number of elements will never change. So that is the best way to deduce what would a dimension change into. Okay. And again, the two-dimensional tensor has been changed into a three-dimensional tensor. Cool. Let's see something along the, what do you say, few other dimensions as well, right? What if we do the same thing? Now what if we add this dim equals to something? Dim equals to 1. What if this happens? So now, simple, eh? It was 2 by 2. We are stacking it along the second dimension. So second dimension has to change into some other thing, right? So let's see what it changes into. So you see it was 2 by 2. In the first scenario, we got what do you say, it just didn't add the both the things up. Okay, in the first scenario it was 3 by 2 by 2. That was the first dimension was 3. We are adding it along. In the second situation it is 2 by 3 by 2, if that makes sense. So I hope you can connect the dots here, that how it's changing. That's all I'm saying. How it's changing. That's all. You don't need to memorize it. You can come back to it. What if we have two? I don't know. I don't know. Let's see. I think it's gonna throw an error, but oh, it works. Okay. So yeah. So 1, 2, 3. What if we have 4? Does it have any? Yeah, that throws an error. Okay. How about 3? It throws an error. Okay. Okay, so we can work with 3 dimension if the even if the original tensor is 2 dimensional. As I said, it changes and added one more dimension, so we can play with these dimensions like that. And I suppose you have some kind of idea now how it's working. You can see what is working, right? Okay. You can have the same thing what we did for stacking, how everything changes with stacking. Again, unsqueezing that bit in the middle, so it would be 2 comma 1 comma 2, then concatenate it along dimension 1, so 2 comma 1 comma 2. Okay, so it's a 3D tensor now, all of them xyz. So it will add one more dimension, so it will become a 4D tensor. It became a 4D tensor, and as I was mentioning, it should be limit equals to 1. So it did this 3 here, right? So it was 2 comma 1 comma 2. The first, or the from, it's a zero index dimensions, right? So one index was uh, stacked along. Okay, cool. uh, See how it's changing. Okay, let's have a look at it. Okay, here in this scenario it was just adding this whole thing up. Nothing crazy happening, you know. Here it was becoming a little hard to visualize what is happening, I guess. This one along the rows, if you think about this, is basically like stacking all these up, right? Check this out. This one, in this one, and this one, all of them are in one big array, you can call it, right? So it's like array of array of array, or list of list of list, whatever you call it. So yeah, and along the one would be simply taking one, see, 159, and okay, this can get really really crazy and complex real fast, right? So along the columns I can see that they're changing it. So this column goes here, and then this column, and this column, and then the next tensor in this scenario has the next columns or the dimensions, whatever you call it. Okay, that's cool. There's nothing crazy here happening. It's just you need to be aware of what kind of transformation am I expecting out of my tensor, and how can I achieve it. Okay, so you know what concatenation is, it's and what stack is. Maybe you forget how exactly is the working, but at least you know what kind of changes will happen if you put this one or put this two into it, right? Okay, there are a few simple ones. I don't know. I'm just gonna put it here. There's nothing crazy happening here, but okay. Repeating the whole thing. So I just take x and repeat it 2 comma 3. So it says that, so this was the actual tensor, right? You remember 2 1 2 3 4 was the actual x tensor. Yeah, see, 1 2 3 4 was actual tensor. I want to repeat it 2 times around the column, that is 1 and see 1 and then this 2. Apart from that, I want to repeat it 3 times along the column. So 2 times along the rows and 3 times along the column. So this one and this one. That's simple. um, I'll repeat the entire tensor. Same thing happening here. Nothing crazy. I don't know the difference here, but yeah, it does the same scenario. Okay, okay, both of them are doing the same job. Okay, I think now comes simple things like indexing. What is indexing? You are just doing it. You have been doing it all along in PyTorch. Nothing crazy. Uh, and another simple Python as well. All you do is try to find one matrix, try to find one element from the an array of element from the copy. So let's say index tensor, these two indexes. Select row number 2 and row number 0 and row number 2, and I put it into tensor. This is the tensor, right? Back into it. What will I get? I will just get those tensors. I will just get the rows and of this tensors. I think this is pretty cool, and you can have slicing. This is what we call slicing. You already familiar with slicing? So it's like take all the rows and take column number 1 and everything after that. Take all the rows along. So this one, all of this. So that's why the shape also remain the same. But column wise, take the first and go along. So this two are there, right? Yeah. Okay. Now this can be nice. Okay. This is create a mask, some kind of a. If you want to create a mask or something, if there's a what do you say, some criteria you want your elements to follow, some kind of a equal than value, so if you say mask is everywhere where the tensor's value is greater than 3, and you put that mask inside the tensor again, so what you get is all the values from that tensor that is more than 3. And if you can see, it has flattened the whole uh, tensor. It just gave you the value in a single array, right? Or a vector or 1D tensor. So many things. Okay, now this can also be pretty cool. Okay, mass selection results. Let's see what happens. Same thing happening here. The same way it's been done there. Okay, that is it. Let's get to the interesting bits of this whole PyTorch engine operation, that is broadcasting. Okay. Okay, what is broadcasting? Broadcasting is it's so in linear algebra. Uh, what do you say? You are not allowed to do some operations like, for example, you cannot do addition of a 4 comma 4 matrix with a 4 comma 1 matrix. So it something like 1 2 3 4. Right, this matrix and this matrix 1 2 3 4, you cannot add it or divide it, or do whatever operations you want to do on that in linear algebra actually, because only you can do addition is of same if it has same dimensions. If it was 4 by 4, then I could do it. So what you do here in this case, in such a scenario, is a PyTorch does, but in PyTorch you can do this operation. You can add, these two. For example, I will show you. Uh, I think I should start with a simpler example that would set your basic things up. Then we can proceed, right? Okay. Okay. Let's take this example. I like this example. Why? Because it gives a very good answers and understanding of the whole thing. Okay. Mm. Let's take the example. Okay. This is your example. This is a 4 by 4 matrix. This is a 4 by 1 matrix. Matrix, no, tensor, sorry. And you want to do element wise division using broadcasting. Okay. So what you want in this scenario is check this out. Okay. Uh, let's take this example also. This is a vector, right? This one was a vector and this was a 4 by 4 matrix, right? And I want to do division of all of them. And if I run this, if it were normal linear algebra, I won't be able to do this. Okay. But here I get an answer. Okay. And the answer seems to be right. Okay. So what's happening here? How exactly is it working? How am I able to do this division? So in this case, what we see here is a matrix. Okay. It's a big time matrix. It's 4, 8, 12, 16, 5, 10, 15, 20, 1, 2, 1, 2, 1, 2, 1, 2. I don't care about that. So it's a 4 by 4 tensor. Coming to the next part, that is a vector. So you are saying I want to divide it with this vector. 2, 5, 6, 7. Okay. So what broadcasting does is it checks the shape of the whole thing. It's if you check its shape would be in PyTorch, it would be something like this. Okay. Comma 1. In PyTorch, it would be just like this. Okay. Oh my God. Okay. Just this. It just shows like a comma here. Okay. Comma here like this. Okay. You see that here, right? Itself. I don't have to waste my time on that. Okay. What it does is it adds the dimension. What it does, it adds a dimension into uh, the vector and then copy the whole thing along the dimension. What I mean by that, right? So what I mean by that is, first important thing, a problem here that lies is it adds dimensions along what it take this vector and it takes this vector and change it for shift it to the right and then add one here. That is what it's doing. That's exactly what's happening. Okay, when you do broadcasting in this scenario, when it's a vector, and what it does then, take the whole thing like this and say this whole thing will be changed into this, and the one that is there, one additional dimension that is added will be changed to 4, what to match the dimension of the first tensor that you are doing the operation on. So this whole thing will change like this: 2, 5, 6, 7. This is the 1 by 1 by 1 by this is basically 1 by 4 of that, right? And you copy the whole thing again. So now it became what? Now it became 4 by 4, and now the division can happen. So this one will be divided by this. So if I do if I see the results of this, what you get is 4 by 2, 5 by 5. Okay, did I make up? Sorry, it's 8 by 5, 8 by 5. This is 12 by 6, 16 by 7. You can just check out what the values are so that we can verify. So 5 by 2 is 2 or something, right? 2. Yeah, I can see the result is 2. 8 by 5 is 1.6. Cool. 12 by 6 is 2. 16 by 7 is 2.28 something something, right? So yeah, it's right, that's how it happens. Okay, so if it's a vector, why I'm stressing on this is if it's a vector, it will shift the dimension into the right and add one more dimension according to the dimension of the tensor or vector or whatever you are trying to do this operation on. Okay, it's important both of them have this ability. Okay, so if I were to state it in a sense, it will be if tensor have a different number of dimension, prepend dimension of size 1 to the smaller one's shape, and then the two tensors are said to be broadcastable if for each dimension the size are equal or one of them is 1. Okay, either they are equal in size or if one of them is 1, then we can do this. Now I guess this was a harder example. The previous one was much easier, I suppose. uh, what I can do is I can take this and this. So now in this scenario, what you have is a 4 by 1 matrix. It's not a vector, it's actually a matrix, but only along one dimension, right? So in this scenario, what we have here is, I'm not filling this out. Oh, sorry. Okay. In the scenario, the same thing happening, but as this is a 4 by 4 matrix, the original one is 4 by 4. The second one is 4 by 1, right? It's already there is 1, right? So what it does, it changed this one into 4 by 4. So this one has been changed. Now what happens is the tensor that was like this, okay, tensor that looked like this would, just give me a second. Okay, just checking my stream. Yeah, so the tensor that was looking like that will sorry. So as it was 4 by 1, so it will look more like this, right? 2 5 6 7, and you are converting this into 4, so you will add this 4 5 6 7, 2 5 6 7, 2 5 6 7, and then this bigger one will be divided. So the bigger one was what, it was something, let's copy from here. See, 2 4 8 12 16. So I am dividing it with this. So if I divide 4 by 2, it will be 2. 8 by 2, it will be 4. 16 by 2, it will be 6. 12 by 6, it will be 2. 16 by 8, it will be 2. And again the same thing happened, right? So that is how broadcasting work. It's a little complex. It can take a little while to sink in what exactly is happening. So it lets you do operations that are not permittable in normal linear algebra class of in mathematics, right? But these scenarios are more often than not are needed. We will come across such scenarios, okay, when we do even next lecture I will be starting with deep learning and mathematics or deep learning and forward propagation, backward propagation, all that stuff is going to come up. So we will be using this. I know at this point it seems arbitrary, why am I doing this, but you're going to use all of this stuff. Coming to the yeah, I guess that makes a lot of sense. I hope what's happening and how it's happening, right? uh, yeah. So as a rule of thumb, if you have two tensors and you want to do some kind of addition, multiplication, whatever you want to do it, if one of the dimensions is 1, you can change it into the dimension of the relative to the dimension of the first matrix, so that you can do all these operations right there. Okay, all this changing is happening internally. See, nothing is happening in the code, right? You are able to take this matrix and divide it by this one. All it does is seriously turns this whole big matrix into, sorry, it looks like this now, right? 2 comma 2 comma 2, and this looks like 5 comma 5 comma 5 comma 5, sorry, and this one comma 6 comma 6 6 6, and this one is 7 7. If I do the same thing, oh, did I make a mistake? Where did I? Okay, there is no need for that. Yeah, same answer. You are getting the same answers from the this one or that one. So instead of writing the whole thing again, you have something called as broadcasting that makes things so much easier. Okay, uh, cool. Few examples of broadcasting, then we will take a small little break, I suppose. These are few tensors. Okay, we're gonna do some stuff on this. Okay. Okay, iska shape. I should print out the shape as well so that you have a reference. It's, by the way, it's all in my notes. You can check out the notes in my comment. I will put it. And let's do something. Now, simple words. You have a scalar phi. You want to add it to a. All the members, all the members, all the elements of the a, right? And you do that. Everything has been added with phi. How does it? How is it possible, right? In reality, in algebra, you cannot do that. You can multiply a matrix with a 2 and it will do element wise. I don't think you can just add this like this. So, but we can do it here. And broadcasting a tensor with a larger tensor. So A is smaller tensor, right? A is the actually bigger tensor. The B is the smallest tensor. As I said, 2 comma 3 and 2 comma 1. So now the 1 will change into 3. When it does, so it will just copy itself along the columns. Okay. So if I print this out, what it did, it copied this one along the column. So 7 by 8, so it will look like something like this. Okay, 7 by 8, it will be copied along. So here will be 7, here will be 7. If I add 7 plus 1 is 8, 7 plus 2 is 9, then again 7 plus 3 is I hope that's clear. So if I go again and do this, okay, what do we have? 1 2 3 4 5 6, right? Now I want to add this bunch here, right? So what it does, simple, as the 1 is here, it's 2 comma 1 and this is 2 comma 3, this number will change into 3, and all you have is you take the whole thing and add it, copy it, 7 by 8 7 by 8, and add them all, you get the same answer. Okay, cool. Next one, broadcasting a tensor to a different dimensions. Okay, let's see what happened here. A and C. What is A? 3 comma 2 comma 3, and this is 3 comma 1, not 1 exactly, it's a vector. So as I told you, the tensor representation is how it is. Okay, so in this case is 2 comma 3, in this case is 3 comma 1, right? As I told you, as PyTorch does not have this one system, does not have this. So what it will do is will take the whole thing to the right and put 1 here, and so now it will be 2 by 3, so that it can do this operation with 2 by 3. So if you check this out, let's see. If you check this out, this whole thing will become what? 2 by 3. So they will be copied along like this: 20, 30, 10, 20, 30. This is the matrix, and this one will the same one, right? 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, 5, 6. Have I mistaken? Have I mistaken? Have I though? No, I haven't. So you see, if you add both of them, it's 11, 22, 33, and all that, right? 10 plus 4 is 14. So that is how it's working. I hope I made myself clear. There is a way. What if you don't want to do this? You want uh how can I put this into, okay, we'll get to that later, when we do actual deep learning. Okay, that's done. What else is there? Broadcasting with a different number of dimensions. Okay. So right now we've almost played with 2 by 2, 2 by 2. And this is also basically same thing, matrix and all. But what if we have a squeeze at one? What if I don't do this? Okay. What if I don't do this? Because that will work with no problem, right? That's pretty simple. What if I delete this and let's test it out? You get an answer. Now let's see what answer that is. And why it is so. So A is 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. The next one that you have here, so it's a tensor. Okay. I'm sorry. Why am I unsqueezing it? You know what? Let's get to this later. Uh, Basically, I hope you understood the whole broadcasting thing. Okay, and already I have completed 40 minutes into the stream. So let's start with Autograd. Autograd is probably the coolest thing in PyTorch, and other libraries also there which uses Autograd. It's not the only one, but I think it's very cool. I think it's neat. Um, okay, Autograd it is. Okay, let's draw a nice line, right? Okay. Then coming to the, let's do this auto. Autograd. Okay, so now here it will be more of a cool stuff. So what is Autograd? So PyTorch lets you do a lot of calculus thing, like not a lot of thing, but it lets you do differentiation in simple words without doing differentiation manually. Like it creates this computational graph, and all it does then is to take that graph and compute all the gradients for all the variables that you want. You can specify which tensor or which variable you want that the gradient to be computed. I know what I'm saying, it makes no sense right now because you actually want to see how it works, right? So we will see an example how exactly it works, and a little recap basically to what differentiation is. Differentiation would something look like in high school stuff. Dy by dx is rate of change, how the y changes with x, right? Simple. Or there's some other way to think of is that whatever the function is, if you have a function like this, if you take the derivative at one point, it would be a tangent along that point, and it defines the slope of that point at that point of that. This is function f of x, right? And this is that dy by dx element. Okay, so this is also one way to visualize dy by dx. Okay, or differentiation. And few formulas if you want me to reiterate: x to power n, sorry, it would be something like n x to the power n minus 1. Simple, right? Um, that's all. There are a few other formulas that you can look into. Okay. Things are gonna get a little too much maths here now. I'm already telling you that because I'm gonna solve few stuff. Let's take this example, the second one. Okay, this one, this the whole thing. Okay, this example. Uh, should I go with this, a smaller one? Okay, this one will be better because I feel it's smaller and good one. Okay, now what we have here is a tensor that is having value 2. X is equals to 2. That's it, right? And y is equals to x to the power 3. That's it. If I were to ask you what is dy by dx, you would directly say it would be 3x square, right? And what would be this value? Because we have the value of x, right? That is 2. I can put in the value and it would be 12, right? Cool. So I got the value dy. What is dy by how the y changes with x by putting the value and got the answer. But what PyTorch lets you do is I've already done a lot of these things. You know what? I'm gonna delete. No, I should not. Okay, give me a second. Okay, cool. Let's try this out. This is the tensor that we have. It's 2. This is y. As soon as you hit y dot backwards, it computes the gradients for all of them. And then you can see one more thing. Remember, the require grad equals to needs to be true. It's not defaulted as true. That's why you have to give it as true, because this value, which is as false, this value is telling the function that I want to compute my gradient for x. So you see the xy, we are basically differentiating with x, right? So I want to do this it's telling that I want to take the function and get the value or the gradient with respect to x, or differentiation with respect to x, whatever you call it, right? Gradient is basically a fancy word for differentiation. When it comes to matrix and all that, we give if there's a list of gradients, a list of derivatives, we put it in a gradient. We will come to that. Oh, what happened? Launch is not depend. Okay, give me a second. So basically, I'm doing is running this through my interactive Jupyter notebook. All I have to do is copy it and running it here. So as I run it, you can see the code is coming here and the tensor is 12, which is exactly what we have here. So what basically it is pretty simple. All it lets you do is calculate the gradients. Let's take this example. This one. Now it's more of a composite one, like there are flow is happening there. For example, here x equals to 1 and y is equals to x square, and then z is equals to y by plus x. So I can write so if I do now z dot backwards, if I do this, what it will do is it will calculate this as I have given. I haven't given actually in this case. I should have here. That should be something required. Let's go to true, true, right? If I do that, now what it will do is it will calculate dz by dx. Now how will you get dz by dx? Simple hai. You have to take chain rule, dz by dy, because it depends upon y as well, right? And dot dy by dz. You can easily calculate that. What is dy by dz? 2x. Okay. And in simpler terms, we can also come up with a easier solution to the whole problem as well. If we go with this, you will get z equals to x. Yes. Okay, give me a second. So you can put here also, okay, this one. So z will become x square plus x. Cool, if that makes sense, because it came here and all you have to do is dz by dx. So 2x plus 1. Now what is 2x is 1, so it will be 3. 3 should be your answer. 3 should be your answer. Okay, if I do z dot backward, and that is it, and then print out xgrad, take this all, paste it, we got 3. Okay, I hope that made sense. Okay, uh, so let's start again with the whole thing. Okay, okay, let's go on. Take few more examples and we will now let's say there are two variables you want to keep track of. Z is a function of two variables in this scenario, right? Let's solve this one out. So x is equals to 2 and y is equals to 3. And the equation that we have is x equals to x into y plus y to the power square, right? And all I do is, now here as we have two variables, we can do partial differentiation on x and then partial differentiation on partial differentiation on y. What is partial differentiation is, basically you keep whatever you are differentiating with. For example, in z you are differentiating with x, so you keep other variables constant. So in this case the y will be constant. We are taking it as constant. It's not constant, we are taking for this partial derivation. So it will become y because it's a constant, right? And this will become 0. Cool. That's just a constant. In this scenario it will become x plus 2y. Cool. Does that make sense? Okay, so if I take this, you will have, what is the value of I? 3. So for, if I take x dot grad, it should give 3, and dz by d, it should be what? X is 2 and this is 2 into 3, that is 2 plus 6 equals to 8, right? So y grad should be 8. That is what I am doing. Okay, 3 and 8, that's what we got. Okay, see, back propagation, why it's needed, Autograd, why it's needed is because of back propagation. So the actual updates, the training happens while the back propagation happens. Okay, so network is flowing, your neural network is there, right? You made it. Now the data goes through network and spits out some output. Now you have a loss function in at the output. What loss function tell is the error between the actual input that you have as a label and whatever the model predicted. Now I want to tune my parameters inside the network so that it resembles the output that is from the actual data, right? Kind of mapping the input and output. So these parameters can be like knobs that you can tune. So the tuning happen, the change of parameter, the learning happens while it's going in the back, while in the back propagation state. All it does is it updates this what do you say, parameters, why they're gradients. We will come into that. We will have a good lecture on what deep learning is and how the network flows. There, every dots that you are finding right now will be connected. Okay, cool. So you got x grad, you got y grad. Cool. We will come to that. Now things are getting interesting, okay? Because now we have a matrix. A matrix, a 2 by 2 tensor, whatever you call it. It's hard to calculate this, okay? This one is hard to calculate because you have to calculate a Jacobian matrix, and I can show you without Jacobian also, but mostly you have Jacobian when you have to differentiate a vector with a vector, a vector with a matrix, or matrix with a matrix. You have to create a Jacobian vector. That's the only way to do it. Now this whole operation, a and b, both of them have require grads, okay? And you are doing matrix multiplication on that c, and you summing up all the c. all the elements in the C. Okay, just so you know, you cannot do this backward on a matrix or a vector or anything. It can only be done on a scalar. So as you add some, it just gives out a scalar, right? This is one value. So make sure that you know that you cannot do this backward on any intermediate state. For example, in this scenario, C is a matrix multiplication of A and B. So it will be again a 2 by 2 matrix, right? You cannot do C dot backwards. It does not work like that. Okay. One more thing you can know is when you have this require grad equals to true, that's called now this is a leaf tensor. It's a naming convention. Okay, it's called a leaf tensor. Cool. And yeah, so we are gonna calculate, do some real good maths here. It's gonna be a little mathy. What do you say? Okay. Now a I'm gonna denote everything as with this suffix. Okay, ij a12 a21 a22. I am prone to make mistakes. I have seen that when I do this kind of stuff, I tend to do some kind of mistakes. So bear with me. I will try to do my best. Cool. So now what would C? So C can be uh, what would you say? Um, hmm, okay, give me a second. There's a way to represent C, and that way would be to simply yeah. So where were we? CKL. Okay, CKL can be represented as summation of M A of KM B of ML. Why do I say that? Because think of this, okay? If I were to say A11, it's like this C11 here. Sorry, AKL, right? KL. Sorry for that. CKL. So it will be C11, C12, C21, C22. Now C11, let's see what the C11 is. C11 is basically the matrix multiplication, right? It's a matrix multiplication. What is C? C is basically a matrix multiplied. Matrix multiplied. So I can write it like this. So this matrix multiplied. So this row along this column. So I can write it down like A11, B11 plus A A12, B21. This is C11. Then I can write same way. I can do this. Okay, A11 B12 plus A12 B22. Cool. That also works. Here coming in A21 B11 plus A22 B21. A21 B12 plus A22 B22. So you can also get the same thing here. Okay, if I were to say you can do the same thing here. Like for A, if it's 1 1, then it will be firstly it will be summation of along M. M is going from 1 to 2, right? So it will be A K 1 B 1 L plus A K 2 B 2 L. So if I put 1 1, that is K and L's values, A11 B11 plus A12 B21, which is exactly, if you see this one, this part is exactly the way same this one. So the matrix multiplication can be represented like this. In books and all, they represent it like this. Okay, so M is going from in this scenario 1 to 2 because there are just two shapes, right? Okay, cool. Now, let's get to the interesting bit. What is D? D is simple, right? D is summation of all the elements in C. What is the elements in C? C11, C12, C21, and C22, right? That is it. And what you want is dabba A, and dabba D by dabba B. That is all you want, right? Now, coming to the point here, I can do a simple mathematics. There are two ways to go about the same thing, okay? And it can get a little overwhelming, okay? So bear with me on this one. Can I say, can I put some chain rule into it, right? D is there, right? If I put like this, is there any harm? Sorry, I can write it like this, right? Cool. Remember, it's a matrix, okay? D is just number, but both of them are matrices. Cool. Yeah, that makes sense. So if I were to write all this stuff up, it will become a Jacobian big matrix and all that stuff. Okay, so I'm gonna write it here first, what it looks like. D, okay, and Aij is equals to summation of KL say along the KL, and D, it goes summation of KL into CKL divided by summation of Aij. Okay, that seems crazy, right? So let's break it down. Let's open it up, right? So Aij will, let's open it along KNL. So if I were to open it along, that's summation along the KNL dimensions. So it will be dabba D by dabba C. What if K is 1, 1? Both of them are 1 and 1, right? One scenario. KL, this is Aij. So KL is, sorry, KL we change into 1, 1, right? So we don't want to use that. Rather, we will use this dabba 1, 1. Oh, again, I made a mistake. Plus, the second scenario is D dabba 1, 2, C12, Aij. Again, add it dabba D C21, C21 divided by dabba Aij. Okay, I hope that made sense. Okay. Now, there's one more. The last one. 2, 2, 2, 2 divided by Aij. Okay. Now, can you find this out? Can you find this ones out? Pretty simple, right? You have the D, you have the C. They are straight. Use this one. So if I put D divided by C11, all I am doing is D of all these C11 plus C12 plus C21 plus C22, and divided by just one of those C11. So it will just give out 1 because all the other will become 0, and this will become just 1. Okay, because they are constants. It's a partial differentiation, right? So this will become 1, this will become 1, 1, 1, 1. Cool. Okay. Okay. All that became 1. So the finally what we have, dabba D by dabba Aij is nothing but function of C11 divided by Aij plus 1, 2 divided by Aij plus 2, 1 divided by Aij plus C22 divided by Aij. Cool. But here is where things gets seriously crazy. Okay, because I can have 4 different values for INGs, right? So now if you check this out, you have 4 different values. For example, if I have first scenario is dabba j dabba a11 is there, so it will be c11 a11 plus c12 a12 plus c21 a sorry a11 is there, right? A11, we are just opening it with a11 a11. Cool. Cool. So now all I have to do is find this, which is very easy to find actually. We checked out. If you check out the C matrix, you will find that we already have that. See, C11 is equals to this whole thing, right? C11 is this whole part. So why don't we just try to find that out? Okay, I can take, so C11 is nothing but one part we are taking it out. A11 B11 plus A12 B21. Cool. Divided by A11, which makes it, this thing will become 0, nothing is there, this thing just become V11. Same goes with this one, A12 divided by A11. Again, do the whole thing. So I am gonna copy this, I'm gonna take this first and where is it? Yes, lasso it, copy, and paste it here somewhere. So we have a reference. Okay. Now, if you check this out, check it out. So this one will directly become, take this is the part. Okay, C A11 if you go is B12. Next is C 21 A11, which is is there A11? No, so it's become 0, and the next one also will also be 0 actually, because it is not 0. So now that's for one of them. The second scenario would be dabba d by dabba A12. In this scenario, again, you have 4 of these, right? Okay. And you got all that things happening and you add them up. For example, I wanted, the final idea was to get these guys, right? The final thing was to find these and this one and this one. So as it's a matrix, there are going to be individual elements. Okay. So A11, A12. So basically there are 4 possibilities that we are trying to find here. This was those 4 possibilities. This is one possibility. This is second possibility. The third one would be D comma A21, and the fourth would be D comma A22. And we are able to find all of them. For example, we already found this one, right? This has changed. This has become 0. This has become 0. This has become A11, and this has become A12. And all I have to find is A12 and A11. What is the value of A11 and A12? So B11 is sorry, B11, I'm sorry for that. So this is 2, right? So I can just put dabba D divided by dabba A11 equals to 2 plus, what is B12? That is B first row, second 0, right? So it will become 2. So in the final matrix of D grad, if you say A grad, sorry, it will become, this is 2. We don't know about this. This 3 will be found by using this one, and this one. So 2 is there. And if you check, yeah, the 2 is coming up. Cool, right? If I were to do the same thing, for A12, now, what do you say? A12 is there, right? So this part we are finding for this one. A12 is there. That is this. Okay. A12, one by one we will have to find all the C1 dabba C11 divided by dabba A12. If you do A12, you will be left with B21. So if I were to do the same dabba A12, it will be B21 plus next one is this dude. So A12 is here, A12 is here. So it's B22 plus 0 because again A12 is not here in anywhere, right? So directly you get what is B21, second row, first column, this one, 2. What is the final one? Sorry, it's 1 and this is 2. Let's make it 3. As you can see, we have 3 here. So that is how you go about finding this. There's one more way, that's called Jacobian way, okay? So this is gonna be this actually helps you to find the, for example, if you had this scenario, right? You had some k and l and you wanted to find some ai of j, okay? So you create a matrix of that. What you do is C11 divided by A11, C11 divided by A12, dabba C11 divided by dabba 21, C2, no, sorry, 11 divided by dabba A, so A here, okay, A, sorry, A22. That's one column. I think I made it a little slow. Okay. I'm gonna do something is make a bigger one. So now on, I will not do this dabba and all. I will just write the name. So C11 divided by, so it's a C12 here. C12 divided by A11. C12 divided by A12. So, or you can write C12, C1. I mostly do this. So, and this one and this A22. Same goes with again this here, 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 here. So now you have a matrix that you can seriously do anything on. For example, if you want to find dabba D divided by dabba in this scenario, in this case, okay, dabba A11, all you have to do is add this column up. If I literally take this into a, let's say it's a what do you call, it's a T, it's a T matrix, big T matrix, okay? All I have to do is take this T dot sum, and I want to sum along what? Along the columns. So we don't have to put anything, right? So along the rows, sorry, it has to go through rows, and it will give out 1, 2, 3, 4. So the sum of this dude will be here, sum of this dude will be here. So what is these dudes? So dabba A by dabba A12, dabba D by dabba A21, dabba D by dabba A22. See, so if you add this girl, you will get this. If you add this one, you get this. If you add this one, you get this. If you add this one, you get this. So if I do that simple term, I get the value of all these ones, and then I can use it if I want to. But this is what we call Jacobian, okay? Jacobian matrix used for when you have like vectors. So this is a tensor, this is also a tensor of, this is 2 by 2, this is 2 by 2, right? It can also be a vector. Same application will be there, same way you will write the whole thing up, okay? So I hope now you understand how tensors are working behind the scene, what the mathematics probably. Okay, let's do some small things, like you can find it on any kind of operations, okay? By the way, one more thing, I want to show you a computational graph. This is a computational graph of that. So if I take the computational graph of this, this one is a good one. Okay, this one works fine. This one goes like this, okay? So it take the x, it has the x. I guess it's not this one, it's this one or this one. Both the same, okay. Okay, it goes inside computational graph. Okay, this one. So telling you what kind of operation is going on. First, x is a accumulated gradient, which we say, and then it goes through a paw. Paw is basically power operation, right? So there's a power operation happening here, And there's also x that goes here also along with x, right? So this power operation through also it goes, and then directly also it goes into this addition operation between this grad, that is this x, and the power operation, that is this y. So this is what we call a computational graph, and you can solve it using this also. I urge you to do that. Okay, cool. So 2D is done. What if we have a tensor, you pass through a activation function, real user activation function? We will look into that. Its formula is pretty simple. You can, and then take a sum. You can also find its C. So as it was a tensor, it gave the grad for each element inside the tensor. That is an important point. Okay, for example, this was 2 by 2 matrix, and all the element inside it, we were able to find the gradient for each element, right? The gradient at each element inside a tensor, not just for this was just a scalar, right? So we were just taking one values. Here all the values have their own gradients. Here also, see, all the values have their own gradients. You can see the gradients at that point. Okay, coming to, okay, this is one more same thing happening, nothing crazy. Okay, this was our testing something out. Let it be. Now this is a complete loop for, what do you say, grade, a simple neural network, simple linear neural network, which is used for regression at this point. I feel like I need to first complete deep learning basics to even get to this point where I will be explaining every single thing, every single line, all the scenarios that you will go through, how these things are built. See, this is a code which is written without using any PyTorch functions. Like this is using this PyTorch functional optimizers and all that, classes and all modules, but this one does not use any of them. Just pure mathematics. Okay, and a training loop, and how, see, these gradients are used in this loop, how they are used to update the parameters. This is where the updation is happening. Okay, this is where the computational graph is created, and gradient is calculated. So all these things will come up in the future. uh, so that's it for today. We will see the next time.